Alrighty, hello everyone, and welcome back. So tonight we are finally going to start talking about the planets as they are today, instead of just talking about the formation of all of them at once. So tonight and next week we'll be talking about the terrestrial planets. Tonight is the geology of the terrestrial planets, and next week will be the atmospheres. But even though we're only talking about geology tonight, there is still quite a lot of material to go through. So in the interest of time, there won't be any question slides, little quizzes in this lecture. But definitely let me know if you have questions in the comments below or direct message me. Without further ado, let's go ahead and get started with tonight's quote, a beautiful one from Ralph Waldo Emerson. Nothing is rich but the inexhaustible wealth of nature. She shows us only surfaces, but she is a million fathoms deep. So if we look at our own Earth, the Earth appears to be pretty solid, doesn't change much, but anyone living in some of the states of the United States would tell you otherwise. If you've lived in Alaska or California, you've definitely felt earthquakes. If you lived in Washington State, you might have been around for the eruption and rumblings of Mount St. Helens. If you live in Hawaii, you live on an active volcano. That reminds you that Hawaii is nothing but a bunch of volcanic rock protruding from the ocean floor. But these volcanoes and earthquakes aren't even the most dramatic changes that occur on Earth. Of course, if an asteroid or a comet impact Earth, that'd be a pretty dang dramatic change. Of course, there's also more gradual processes. So like the Colorado River, the erosion caused by that water carved out the Grand Canyon. And of course, over millions and millions of years, even the continents gradually moved about, colliding into each other to make mountains, splitting apart to create valleys, until we get something that resembles the world as we see it today. Now, the Earth is certainly not alone in experiencing these different processes. All of the terrestrial planets, including the moon, we'll add the moon into our talk tonight and next week, have undergone this whole change. So Mercury and the moon show the scars of their battering during their heavy bombardment. They're densely covered by craters, except in areas that appear to be volcanic plains. Bizarre bulges and odd volcanoes dot the surface of Venus, and Mars, despite its middling size, has the solar system's largest volcanoes and a canyon that stretches 1/5 of the way across its surface. And of course, Mars has numerous features that appear to have been shaped by liquid water. The Earth has surface features that are similar to all those on the other terrestrial worlds, including a very unique layer of living organisms that cover almost the entire surface of the planet. So our goal tonight is to understand how these differences among the terrestrial worlds came to be through the study of planetary geology. So first, let's talk about the insides of the planets, their cores. And so we want to answer the question of how do we know what the insides of the planets are? Obviously, we can't actually drill down to the core on Earth. We certainly can't do it with the other planets. We don't live on those other planets. We have to infer their composition and their structure through other ways. For the Earth, most of what we know about the interior comes from seismic waves. So earthquakes, those vibrations that travel through the interior and along the surface. And there are two types of waves. There are P waves called pressure waves, primary waves, and S waves, secondary waves, or shifting waves. Those S waves can't travel through liquid. So when an earthquake happens, on the other side of the world from the earthquake, we should still get those P waves that can travel through liquid, can travel through liquid. However, we don't get the S waves, which means there must be something in the center of the Earth that is relatively liquid. So that's how we know about the Earth. We also more recently have seismic data for the moon, thanks to the seismographs that the Apollo astronauts left behind. And more recently on Mars, thanks to the Mars InSight mission, which I think only landed there in 2016. I could be wrong, but around then. For the other worlds, Mercury, Venus, we got to use some less direct methods. So for example, if we compare the average density of the planet, remember that's just the mass divided by the volume, to the density of its surface rock, that can give us a clue to how dense it must be on the inside. So when I start talking about these inner layers of plants, this is how we know, this is how we can deduce those inner layers, the compositions and their structures. So planets are sort of like ogres and onions. Our studies of these interiors have shown that they are layers. At the very center, we have the core, shown here in gray in this diagram. Excuse me. The core is the highest density material, and it's primarily metals like nickel and iron, really heavy stuff. Surrounding the core is the mantle, and this is more rocky material, moderate density, mostly stuff containing silicon and oxygen, and it surrounds the core. And of course, above the mantle, the part that we live on is the crust. It's the lowest density material, stuff like granite and basalt. You can think of it as all of the world's outer skin. Now you can certainly see in this diagram that there are differing sizes of cores, different proportion of mantle to core among all the planets and the moon. And we've got to explain that. But first, why are planets like ogres and onions? Why are they layered like that? Well, we explained that through the process of differentiation. And no, this has nothing to do with calculus. That's a completely different thing. So it has to do with densities. Gravity will pull the denser materials towards the center when everything is all molten and liquid during their formations. Gravity will pull the denser materials towards the center. So that dense material like iron and nickel will sink towards the center, whereas the rocky stuff like silicates and granite and basalt will stay and float on the surface. It's very much like this stereotypical cylinder of different materials, all balanced delicately based on their densities. And we see this in our studies of the Earth's interior. This is the standard Earth model. That's not the real name for it, but it's what we all assume the Earth to be. And you can see on the horizontal is the radius from the center of the Earth. On the vertical is the density. You see the crust in red. All the way out here has the lowest density. Remember, it's low on the plot. The mantle, slightly higher density. The core is actually split up into the inner and the outer core here on Earth. The outer core, slightly lower density than the very dense inner core. So we do have models, we do have data to support this sort of theory about differentiation. Often, however, it's way more useful to categorize the interior layers by their rock strength rather than density, because rocks can slowly deform while under stress and heat. So that means that even solid rock will deform and flow over millions and billions of years. The outer layers, in that way, the outer layers are cold and rigid rock, which is called the lithosphere, which is essentially rock that is floating on the warmer, softer rock underneath. So you can see the dashed lines here show you the rigid lithosphere. So the Earth and Venus have a relatively small lithosphere. Mars and the moon have really big lithospheres, almost to their cores. Mercury has a very small lithosphere, but it still reaches to the core because the core is really big for a planet Mercury's size. And that thickness of the lithosphere is very important to geology. Because it's related to the size of the planet. Smaller worlds have larger lithospheres. And so the thicker the lithosphere, the less likely molten rock can escape from below. So you can probably start thinking ahead that because Mars and the moon all have pretty thick, both have pretty thick lithospheres, there's not going to be a lot of volcanic activity on Mars and the moon today, at least. Maybe in the past, but not today. All right, so most geologic activity comes from internal heat. And that heat is typically generated from 3 different sources. So accretion is the source of internal heat during its formation. Because remember, conservation of energy, we're taking gravitational potential energy, converting it into kinetic which is later converted into thermal energy. These different asteroids and comets impacting the planet is adding heat by just converting their energy into the planet's heat. Differentiation is also a source of heat because as the dense materials fall to the core, they are also converting their gravitational potential energy into thermal energy via friction with all the other material around them. Remember, because the light elements the lighter material have to move up from the core because they're less dense. And then radioactive decay is by far the most important form of generating internal heat today, because radioactive isotopes like uranium or potassium or thorium will decay, and those subatomic particles will fly off and start colliding with the neighboring particles, converting some of that mass energy into thermal energy. Accretion and differentiation were really only important in the early history of the planet. There aren't that many impacts today to give planets enough heat through accretion, and differentiation has pretty much all but completed. All the planets are pretty fully differentiated. So only radioactive decay is that continual source of heat. Now, how do we get that heat out? Well, we've got to transport that heat outward from the hot core through the warm mantle to the cold crust. And that happens through three processes. You've probably heard of all these three heat transfer processes. So we've got convection, where hot material will expand and rise while cooler material contracts and sink. This happens whenever you boil a pot of water. The bottom of the pot heats up the water. That hot water rises. Once it reaches the top of the surface of water, it will cool, and then that water will sink, and repeat this process over and over again. This happens inside the mantle of planets. Then conduction is where heat is transferred via physical contact. So, for example, light bulbs, you don't really feel the heat, but if you were to go touch the light bulb while it's been on for a while, that is conduction. You would immediately feel the heat. And then radiation is, of course, we talked about this before a few weeks ago. All objects emit radiation depending on their temperature. So light will carry energy away. For the Earth, convection is the most important process until that heat reaches the lithosphere. Remember, that's really rigid rock. At that point, conduction will dominate until it reaches the surface, where radiation will then take that heat away from the Earth and out into space. Now, size is the primary factor in determining geological activity. Larger planets simply can hold on to heat longer. So that means that the small sizes of the Moon and Mercury meant that their interiors cooled within 1 billion years of formation. So therefore, their lithospheres grew. Lithospheres continue to push down towards the core, pushing that mantle deeper and deeper. As a result, both are geologically dead. Magma can't get out of the lithosphere to have volcanoes happen anymore. The lithosphere is also too rigid for earthquakes to really happen. So they're not doing tectonic plate movement. They are both geologically dead. The Moon and Mercury are both pretty much dead. Earth is the largest terrestrial planet, so it's large enough to where it's have stayed hot for about 4.5 billion years. Venus is only slightly smaller than the Earth, so it's probably still as geologically active as Earth. Mars is the one that's the most interesting because it's obviously bigger than Mercury, but smaller than the Earth and Venus. So that intermediate size makes it sort of an intermediate case. It's probably cooled significantly, but it might still have some retained internal heat for some geological activity. We'll talk about all of these planets in specific towards the end of the talk. Right now, we're just getting our bearings about what the planets are doing. And of course, it's very much what's on the inside that counts. That interior heat creates a global magnetic field. So the Earth's magnetic field is obviously most well known for telling a compass which way north is. But it also creates a magnetosphere that surrounds the planet and diverts the paths of high energy charged particles coming in from the sun. Therefore, the magnetic field protects the Earth's atmosphere from being stripped away into space by these charged particles. This is probably what has led to our existence. Just the fact that Earth has a magnetic field to protect its atmosphere led us to evolve to be here on Earth. You're probably most familiar with the pattern of a bar magnet. If you look at iron filings around, that's what's there on the left image. Earth's magnetic field is generated by a process that's more similar to that of an electromagnet, in which a magnetic field arises as a battery forces charged particles to move along a coiled wire. Earth obviously does not contain a battery or coiled wire within it, but charged particles do move along with the molten metal in its liquid outer core. Internal heat causes the liquid metal to rise and fall. Remember, that's convection, while Earth's rotation twists and distorts that convection pattern. And the result is that electrons in the molten metal move within Earth's outer core in much the same way as an electromagnet, which generates the Earth's magnetic field, which you can see on the right. You can see the field lines are very similar to the field lines of an electromagnet. And there are three basic requirements in order for a planet to generate a magnetic field. So first, you've got to have an interior region of electrically conducting fluids, such as a molten metal. You need convection in that layer of fluid, and you need some amount of rapid rotation. And the Earth is the only planet that satisfies all three of those requirements. So the moon has long since cooled and has completely stopped convecting. Mars's core is probably still hot, but it's not hot enough to drive convection. Venus probably has a molten core, but either its convection or its 243-day rotation period are way too slow to generate a magnetic field. Mercury, on the other hand, is really weird because it does have a magnetic field, and we don't know why. It might be because Mercury has a huge metal core, which may still be partially molten and convecting, but it should have cooled a long time ago. We're actually really not sure why Mercury has a magnetic field, but it does. It has a slight one. But really, the Earth is the only one that has a major magnetic field among the terrestrial planets. Now, when it comes to the surface, we've talked about the interior now. Now let's talk about how we can shape the surface of these worlds. Most surface features can be explained by four major geological processes: impact, cratering, volcanism, tectonics, and erosion. So impact craters, as you probably would know by now, it forms when an asteroid or a comet slams into the solid surface. Usually at speeds between 40,000 and 250,000 kilometers per hour, or 25,000 to 155,000 miles per hour. This will vaporize the solid rock underneath it, and it will blast out a crater, sending debris raining down over a large area on its surface. Craters are usually circular, regardless of what direction the impactor came into. And they're usually, a good rule of thumb is that the crater is usually about 10 times as wide as the objects that created them. And they also might contain a central peak from the rebound. So just like a drop of water into a nice flat pool will sometimes bounce back up. The same thing can happen with rock. That is how, vaporized the rock becomes when it impacts a planetary surface. So on the left there, you can see Meteor Crater in Arizona, a relatively recent crater, about just under 4,000 feet across. Meanwhile, on the right, you can see one of the more well-known craters on the moon, Tycho Crater, about 54 miles across with a central peak right there in the center. So those are two great images of craters. And then looking at the crater itself can also tell us clues about the geological conditions. So, for example, the leftmost crater has a simple bowl shape. It's a basic crater. The middle one has an extra bump in its center, and it appears to be surrounded by some mud flows, suggesting that underground water or ice melted or vaporized on impact, and then that muddy debris then flowed across the surface and hardened into the pattern we see today. The rightmost crater shows obvious signs of erosion. It lacks a sharp rim, and the floor no longer has a really well-defined bowl shape. This suggests that ancient rainfall eroded the crater and that the crater bottom was once a lake. Studies of crater shapes on other worlds also provide similar clues to those surface conditions in history. Volcanism, on the other hand, occurs when underground molten rock finds a path to the surface. Molten rock tends to rise for three main reasons. So first, it's generally less dense than solid rock, and lower density materials tend to rise when surrounded by higher density materials. Second, the solid rock surrounding a chamber of molten rock can squeeze the molten rock, driving it upward under pressure. And third, molten rock often contains trapped gases that expand as it rises, which makes it rise much faster and lead to these dramatic eruptions. And the result of an eruption depends on how easily the molten rock or the lava flows across the surface. So lava that is runny can flow very far before cooling and solidifying, while lava that is thick tends to collect in just one place. Broadly speaking, volcanoes can come in three different types. So the thickest lavas can't flow very far before solidifying. And so therefore we get these tall, steep-sided volcanoes called stratovolcanoes. So Mount Fuji in Japan is an example, as well as Mount Kilimanjaro in Tanzania and Mount Hood in Oregon. Those are all stratovolcanoes caused by thick lava that can't run very far. Somewhat runnier lavas can spread some distance before solidifying, creating volcanoes that slope more gradually. These are called shield volcanoes. So these volcanoes can be very tall, but aren't that steep. So the Hawaiian Islands are shield volcanoes, as well as Olympus Mons on Mars. It's a shield volcano. And then the runniest lavas go very far and flatten out before really even making a mound that we would call a volcano. So instead, they create volcanic plains or lava plains. So examples include, say, the Columbia Plateau in Washington State and Oregon, and the vast lava plains that make up the smooth regions on the moon, such as Mare Imbrium on the moon that you see there on the right image. All of the terrestrial worlds show some evidence of volcanic plains and shield volcanoes. Apparently, the lava that makes up those different types, basaltic lava, is pretty dang common. Steep volcanoes are common on Earth, but rare elsewhere in the solar system. But besides creating volcanoes, volcanism can also do something else. The water and gases that were trapped in the rocks during the formation is released in outgassing when these volcanoes erupt. So virtually all of the gas that made the atmospheres of Venus, the Earth, and Mars, and of course the water vapor that eventually rained down here on Earth, was originally released from planetary interiors by outgassing in volcanoes. Tectonics is the other one. Tectonic activity usually goes hand in hand with volcanism because both require a source of internal heat. So the crust sort of just floats on top of the liquid mantle. And so movement of the mantle will cause the crust to push together or spread apart. So compression in the crust causes mountains like the Appalachians or more famously the Himalayan mountains. While stretches of the crust can cause cracks and valleys, like this image from Mars, the Seronius Vase is believed to have been stretches in the crust. We'll talk about plate tectonics way more in detail towards the end when we get to Earth. And then erosion is pretty dang common here on Earth. It's the transport or breakdown of surface rock through ice, liquid, or gases. So erosion is usually thought of as just destroying things, although it can destroy them very beautifully. So the Grand Canyon and Yosemite Valley are example of erosion that has carved out pieces of land on Earth. But it can also build things up. So river deltas and sand dunes is erosion building them up. Those are very beautiful as well. All right. We can also learn the age of a surface. Notice that impact cratering is the only process with an external cause. Everything else relies on something happening specifically to that planet, whether from the internal heat or on the surface caused by wind or water. Impact cratering is the only thing that doesn't matter about the specific planet. It will just happen. And so we can, that leads us to a very useful fact in that we can estimate the geological age of any surface region from the number of impact craters in that region, where more craters indicates an older surface. So, for example, crater crowding varies from place to place on the moon. The highlands have many craters, while the Maria, which is Latin for seas, have relatively few craters. This was supported by radiometric dating the rocks that the Apollo astronauts brought back. And we found out that the highlands are about 4.4 billion years old, while those from the Maria are between 3 and 3.9 billion years old. So you can see the difference here in this image. So on the top is the Sea of Tranquility. It is a lunar Maria. And on the bottom are the Descartes Highlands. And you could just see in these images the differences in the amount of craters between the two images. I didn't pick those just to show this example. You could drag those blue and red circles across any of the regions on the moon. And as long as you picked out a Maria and Highlands, you will see the same difference. So then why do these planets have different geological histories? And there are three fundamental properties that control to what degree each of our four processes affect each planet. So volcanism and tectonics both require internal heat, which means they depend on planetary size. Excuse me. All of the terrestrial worlds probably had some degree of volcanism and tectonics when their interiors were young and hot. But as the interior cools, volcanic and tectonic activity subside. So the Moon and Mercury lack ongoing volcanism and tectonics because their small sizes allow their interiors to cool long ago. The Earth still has active volcanism and tectonics because it's large enough to still have a hot interior. Venus, nearly the same size as Earth, must still be hot and probably still has some active volcanism and tectonics. And Mars, with its smaller size, has much less volcanism and tectonic activity than it did in the distant past. But erosion arises from an atmosphere, from weather phenomena. And so planetary size is also important because erosion does require an atmosphere. And a terrestrial world can only have an atmosphere if it's large enough to have had significant outgassing. And that its gravity is strong enough to have prevented the gas from escaping into space. Distance from the sun is also important because of its role in temperature. If everything else is equal, then the higher temperatures on a world closer to the sun will make it easier for atmospheric gases to escape into space, while colder temperatures on a world farther from the sun may cause atmospheric gases to freeze out. Distance is also important because water erosion is much more effective with liquid water than water vapor or ice, and is therefore strongest when moderate temperature allows water vapor to condense into liquid form. So the Moon and Mercury lack significant atmospheres and erosion because they don't have any outgassing today. And any atmospheric gases that they had in the past has already been lost into space. Mars has limited erosion today. It has only a very thin atmosphere because much of the water vapor and carbon dioxide outgassed in its past either escaped into space or lies frozen in its polar ice caps or underneath the surface. Venus and Earth probably had very similar amounts of outgassing, but cooler temperatures on Earth led to the condensation and the formation of oceans, allowing wind and weather to drive strong erosion. Most of Venus's gas remained in its atmosphere, making it much thicker than the Earth's, but Venus has very little erosion because it's rotating so slowly. And then impact craters are essentially external random events. So planetary factors are not as important, but impact craters can be destroyed over time. And the primary factor there is, once again, size, because larger worlds have more volcanism and tectonics, and in some cases erosion, that tend to cover up or destroy impact craters over time. So the Mercury and Moon are heavily cratered today because their small sizes have supported relatively little geologic activity. Mars has had more geological activity, and therefore has somewhat fewer impact craters remaining today. And the active geologies of Venus and the Earth have erased nearly all of the ancient craters, leaving only those that have formed relatively recently, within the last billion years or so. So recently on a cosmological sense. All right, so now let's get into talking about specific objects in the inner solar system. We'll start with the moon and the Mercury. The moon and Mercury, they are pretty similar to each other. So what geological processes shaped the moon? So the bright, heavily cratered regions, like I said before, are the lunar highlands, while the smooth, dark regions are the lunar maria. However, the entire surface of the moon should have been covered in craters during that late heavy bombardment period. So what happened to those craters in the maria? We think that the Maria formed after those craters or as a direct result of those craters. So during the late heavy bombardment period, craters covered the entire surface of the moon. And in fact, some of them were pretty large impacts, likely strong enough to fracture the moon's lithosphere, which gave it some little cracks underneath the craters. However, the moon had already cooled. So no molten rock immediately filled the craters until millions of years later, thanks to that heat from radioactive decay. That works on longer timescales. So that means that the lava flowed up through these cracks into the craters and cooled. They solidified. Therefore, the Maria are essentially giant filled-in craters. Their dark appearance comes from the basalt that rose up from the interior as lava. And that lava must have been pretty runny because the Maria are pretty flat. Relatively few impacts have happened since, which is why the Maria are relatively craterless as compared to the highlands. The moon today is a pretty dead place. Since the formation of the Maria, there hasn't really been much geological activity, although there is a little bit of evidence for some small eruptions happening as recently as 50 to 100 million years ago. The only ongoing geological activity is the sand blasting of the surface by micrometeorites. These are sand-sized particles from space. These usually burn up in the Earth's atmosphere, but they rain directly onto the surface on the airless moon. And these micrometeorites gradually pulverize the surface rock, which explains why the lunar surface is covered in a thin layer of powdery soil. You can see this as you watch the wheels on one of the lunar rovers drive around. It's picking up that powdery surface. Aside from this micrometeorite sandblasting, the lunar surface has been dead for about 3 billion years. But it's still a very interesting place. All right. So what geological processes shaped Mercury? Well, impact craters are certainly visible all over the surface on Mercury, which tells us that the surface is pretty ancient. However, they are less crowded than on the moon, suggesting that lava did cover up some of the earlier craters. Mercury's largest craters are called basins. So this is an image of the Caloris Basin. This is formed by an impact that's so large and violent that they melt surface rock and then filled up the crater. The Caloris Basin spans more than half of Mercury's radius. In fact, this impact was so large on the opposite side of Mercury, there's some ragged terrain, which might be, rebound shocks from the shock wave going all the way around the planet. Mercury is also oddly covered in cliffs that stretch 3 kilometers high or more and then run for several hundreds of kilometers across the surface. These are called roops. So on the top right is an image of Discovery roops, discovered by Mariner 10. They probably formed when tectonic forces compressed the crust, causing these crumples, which is evidence for the shrinking of Mercury in its past. So you can think of it as this. Remember that Mercury has a much larger core than the moon. Mercury therefore gained and retained more internal heat from accretion and differentiation than the moon, and this heat caused Mercury's core to swell in size. Later, as the core cooled, it probably contracted by as much as 20 kilometers in radius. And so the mantle and lithosphere must have contracted along with the core, generating the tectonic stresses that created these cliffs. Mercury is also thought to have retained internal heat longer than the moon, confirmed by crater counts, but most activity ceased between 1 to 2 billion years ago. But despite that, some crater floors do appear to be leaking some vaporized material, causing the rock to crumble and make hollows. So examples of those hollows are seen in the bottom image from Eberswalde Crater. This is a false color image. They're not actually blue. So Mercury is still a very interesting moon. We don't currently have a spacecraft orbiting Mercury. We'll get one again in 2024 when the European Space Agency mission, Bepi Colombo, reaches Mercury. All right, now the very interesting geology of Mars. So here's a nice topographical map of Mars. I have marked off several features for you here. So the red X's are former missions of former landers or rovers on Mars that are no longer active. The blue X's are current missions that are active on Mars. So Curiosity, Perseverance, and Mars Insight. Those are the ones that are currently active on the surface. And the yellow X's are planned landing sites for future missions. I've also circled a few very important areas. So you can see on the left, Olympus Mons is out there towards the left. The Tharsis Bulge has 3 volcanoes on it. Also, sort of jutting out of the Tharsis Bulge is the Valles Marineris. And there, the bottom right is the Hellas Basin. I should say here as well, the colors indicate the relative altitude. So blue is below sea level, what sea level means on Mars. Yellow is sea level, and red, and then brown and white are above sea level. So you also notice this weird little dichotomy of Mars, that the northern hemisphere is almost entirely below sea level, as opposed to the southern hemisphere. And the northern hemisphere has very few craters compared to the southern hemisphere. So when it comes to volcanism, that's probably very important in erasing those craters in the northern plains. Although we're really unsure why it had such a big effect in the north rather than in the south. One volcano, which you see here, is of course Olympus Mons, the largest mountain in the solar system, with a base 600 kilometers across and a peak 26 kilometers high. Completely dwarfs Mount Everest here on Earth. Makes it look so tiny. If you put Olympus Mons on Earth, it would cover about the size of France or fit comfortably into the Australian outback. It's a pretty dang big volcano. Along with Olympus Mons, there are also several large volcanoes in the Tharsis Bulge, which is a region about 4,000 kilometers across, likely created by this just long-lived plume of rising mantle material that bulged the surface and provided the lava for eruptions. We think Mars had volcanic activity as recent as tens of millions of years ago, and it might still be active. These volcanoes might erupt again in the future. But within a few billion years, Mars will become as geologically dead as the moon and Mercury. Mars also has evidence of tectonic features. So Mars' most prominent feature is the deep system of valleys that we call Valles Marineris, which stretches about a fifth the way around Mars' surface. And it is 4 times as deep as the Grand Canyon. And no one really knows exactly how it was formed. Parts of the canyon are enclosed by high cliffs on both sides, so flowing water or lava couldn't have formed it, but its western end is in the Tharsis Bulge, so maybe there's a connection. We're really actually not that sure. You see I've labeled some of the features in Valles Marineris, this weird system of labyrinthian canyons called Noctis Labyrinthus, or Labyrinth of the Night, all the way through the main canyon, which has two parts up here, then it splits into three, then one larger part before emptying into two other parts. It's a really weird system of canyon. We're not really sure how it was created. Now, of course, the big question on everyone's mind is, was there water on Mars? So first of all, liquid water is completely unstable on the Martian surface. The pressures are too low to keep it liquid. The temperatures are too low to keep it liquid. So it is does like to stay as a solid ice. But any liquid water that would have existed would have still evaporated and escaped into space. However, there are some features on Mars that could only be explained with the presence of water long ago. We're talking 3 billion years ago. So the lack of those small craters, all the craters on Mars are intermediate size or bigger. There's not a lot of small craters. So that suggests erosion. There are features that look like river deltas. Our rovers have found mineral evidence of liquid water in ponds or lakes. Curiosity right this moment is heading towards Mount Sharp, where we think there are actually layers that we can see in the mountains that look like sedimentary rock. And there might be even some evidence for recent water flows as the temperatures warm during the years, the seasons change. So here you can see on the top left features that look like river deltas in the Eberswalde Crater. An image from Curiosity on the top right that looks like sedimentary rock in a dry riverbed. And this little GIF here looks like water is flowing down a hill and then drying up. Like, that's insane. There might still be some evidence of liquid water currently in the soil on Mars. That's absolutely insane. That's why we keep sending rovers there. We keep sending orbiters, and because we want to know this information. And here's a beautiful shot of Mount Sharp from Curiosity. And you can sort of see the layers in the cliff faces that look like sedimentary rock, which can really only be created from liquid water. So that's very, very, very cool. Lots of mysteries, lots of interesting things happening on Mars. Now, we move to the next biggest planet, Venus. Here's another, just like I showed you an image of the surface of Mars, here is a radar image of the surface of Venus, where the colors tell you altitude. So blue and purple are low altitude stuff, then green, yellow, red, all the way up to brown and white are high altitude stuff. Broadly speaking, there are three different, there are three different continents, quote unquote continents on Venus. We have Lada Terra in the south, Aphrodite Terra to the right, and Ishtar Terra up in the north. The red X's are former missions, most of them, if not all of them, Russian, that have landed on the surface of Venus. Lasted for only a few minutes, but they have landed and sent back images. Most of our knowledge about the surface of Venus comes from the Magellan spacecraft, from the radar mapping that spacecraft did. When it comes to impact craters, Venus doesn't have a lot of impact craters. That means that those craters were erased by other processes. It also lacks a lot of large craters, probably because those impactors burned up in Venus's thick atmosphere. So one example of a crater is Danilova crater up at the top right. Venus is also covered in lava plains and volcanic mountains, and it has some evidence of volcanic activity in the past. Some of these features, including large circular coronae, which is Latin for crowns, provide strong evidence for mantle convection beneath the lithosphere. It's probably still geologically active as well. You can see some pancake domes there, which are shield volcanoes. And although we haven't witnessed any volcanic eruptions, at least two lines of evidence does suggest recent volcanic activity. So first of all, Venus's clouds, as we'll talk much more in detail about next week, Venus's clouds contain sulfuric acid. And sulfuric acid is made from sulfur dioxide and water. And the sulfur dioxide must have entered the atmosphere through volcanic outgassing. Because sulfur dioxide is gradually removed from the atmosphere by chemical reactions with surface rocks, the existence of sulfuric acid clouds means that volcanic outgassing must have occurred within the last 100 million years. The second line of evidence narrows the timescale a bit further. The European Space Agency's Venus Express mission, which orbited Venus from 2006 until early 2015, detected an infrared spectral feature from rocks on 3 volcanoes, indicating that they erupted within the past 250,000 years ago, which is very, very recent on a planetary timescale. So Venus is still probably active, and it might erupt any time in the future. We sort of naively expect for Venus to have some strong erosion because it has such a thick atmosphere, but images from the surface suggest otherwise. Venus is way too hot for any type of rain or snow or even other liquid materials to fall onto its surface. And as I mentioned earlier, Venus's slow rotation means it has very little surface wind. Images from the Venera spacecraft, such as this one from Venera 13 in 1982, show a very bleak surface, volcanic landscape with not many evidence for erosion. So there's not erosion on Venus, despite that atmosphere. It's just too thick, too hot, too slow. Does Venus have plate tectonics? That's an interesting question, because Venus doesn't show any evidence of Earth-like plate tectonics. Instead, Venus shows the same age surface everywhere, about 750 million years old, across the entire planet. We think it doesn't have any tectonic activity because its lithosphere is thicker and stronger than Earth's, so it doesn't fracture as easily. And it might be thicker and stronger because Venus's high temperature have essentially baked all of the water out of its lithosphere. So that's why we think Venus doesn't have any plate tectonics, but there's still questions about it. We really want to get more missions to Venus. We're so concerned with Mars right now. We've kind of neglected the 2 innermost planets. And certainly Venus does pose some engineering problems. How do we get a lander on the surface and have it survive for a while so it can give us data back? That is a big engineering question, but something that we hope to do in the future. All right, and now we move on to the unique geology of Earth. Now, as you might have surmised, I am not a geologist, so I will be skipping over a lot of really probably interesting things and getting some things wrong. As an astronomer, I spend most of my time looking completely away from what we're about to talk about. So just take everything what I'm about to say with a grain of salt. So the most dominant feature that shapes the Earth's surface is Earth's plate tectonics. It's the one thing that really makes it stand apart from the other terrestrial planets. And our theory about plate tectonics can be traced back to one guy, Alfred Wegener, in 1912, who proposed the idea of continental drift by noticing that South America and Africa seem to sort of fit into each other. You can see here, this part of South America can sort of fit into this part of Africa. And he's essentially right. However, his idea didn't gain traction at first. It only gained traction when geologists started to discover these mid-ocean ridges. Oops, I thought I had a picture there, which shows that the seafloor grows, causing the continents to drift apart. So here you can see all the different continental plates of the world. The mid-Atlantic ridge is this black line here, going here between the North American and Eurasian plates in brown and green, then along the African plate, and then along the South American plate, all the way down here to the Antarctic plate. Now notice this brings up, how do I define a continent? Because not all the plates have continents on them, and some of the plates contain multiple continents. Some of the plates split up continents into plates. So, for example, Africa is all on one plate. South America is all on one plate. North America is a bit split once we get down to Guatemala. Europe and most of Asia is on one plate, but break off Saudi Arabia and India into one plate. Australia is pretty large. Antarctica, we got the Pacific plate. The Philippines has its own plate, and then there's a bunch of smaller ones here along the Pacific Ocean. The Juan de Fuca, Cocos, the Nazca, the Caribbean plate, the Scotia plate. It really makes you think, how do we define a continent? Which we won't get into. There's a beautiful video out there on YouTube for you to watch, but I won't get into that here. Earth is unique in that it has two types of crust. We have a seafloor crust, which is thinner, denser, and younger than the continental crust. So the seafloor crust, or the oceanic crust, is typically about 5 to 10 kilometers thick and made of high-density basalt rock. And radiometric dating has shown that it is less than 200 million years old. Meanwhile, continental crust is typically 20 to 70 kilometers thick and is made of low-density rock like granite. And in some places, like the Canadian Shield, it's around 4 billion years old. This is going to be very important for the conveyor belt that is plate tectonics. So remember, the mantle is doing all this convection. It's got these convection cells where hot rock is moving up, cooler rock is moving down. So mid-ocean ridges, like the Mid-Atlantic Ridge, occurs at places where mantle material is rising up, creating new seafloor crust and pushing the plates apart. Over millions of years, that crust gradually makes its way to the other side of the convection zone, towards a subduction zone, where the seafloor meets the continent. And because the seafloor crust is denser than the continental crust, the seafloor slides underneath the continent back into the mantle, thus destroying that crust, but refeeding the mantle. As the seafloor crust slides in the mantle, if enough material melts, then that molten rock may erupt upward as a volcano, which explains why there's so many volcanoes along the edge of the Pacific, the Ring of Fire, because all around there, go backwards here, all around here, you see the two red arrows pointing together. Those two plates are colliding, and the oceanic plate is going to slide underneath it, building up magma and causing volcanoes. So all along this black line, you'll see tons and tons and tons of volcanoes. It's the Ring of Fire. Clearly, plate tectonics is driven by the heat flow from mantle convection, which makes internal heat very, very important for plate tectonics, which explains why the Moon and Mercury don't have plate tectonics, explains why Mars doesn't have plate tectonics anymore in more recent history, and why it's so confusing why Venus doesn't have plate tectonics. Now, we've talked about destroying the ocean floor. Continental crust, however, does not get recycled back into the mantle. As a result, the continents have been built up over billions of years, but they're continually reshaped by volcanism and stresses of plate tectonics, as well as by erosion. So here is sort of a geological map of North America. You can see, starting off of the East Coast, the Appalachian Mountains were formed by repeated collisions with other continents. The Deep South has some deep sedimentary layer formed by erosion of the continent, which makes it very good for planting crops, which is why there's such a strong farming economy down there. Up in the Canadian Shield, you can see a bunch of lakes, which means this area is heavily eroded. This is really old rock. The plains and the Midwest of the United States is where sediments were deposited from ancient seas, which were later then turned into rock. Most of the Rocky Mountains were formed more relatively recently from plate collisions. And then some former Pacific islands have emerged into the continent to create subduction, particularly in Washington State and Oregon. So tons and tons of processes go into building these continents. And eventually tons of processes will go into tearing them down. Continental plates build each other up when they collide, but they can also pull apart or slide relative to each other. So when continental plates pull apart, we get rift valleys that will eventually tear the continents apart and form an ocean. So the East African Rift Valley is a very good example. That rift is slowly growing and will eventually tear the African continent apart. At that point, rock rising upward with mantle convection will begin to erupt from the valley floor, creating a new zone of seafloor spreading. A similar process tore the Arabian Peninsula from Africa, creating the Red Sea, which you see right here up at the top of this figure. The Rift Valley process is also active in New Mexico's Rio Grande Valley. When continental plates slide past each other, we get faults where the stress is sometimes so great that earthquakes happen. So the San Andreas Fault, which that's a picture of here, the bottom one, marks a line where the Pacific plate is moving northward relative to the continental plate of North America. In about 20 million years, in fact, this motion will bring Los Angeles and San Francisco together. But those plates don't slip smoothly past each other. It's like rubbing two pieces of sandpaper together. Their rough surfaces sort of catch on each other. And so stress will build up until it's so great that it forces a rapid and violent shift, causing an earthquake. And in contrast to the usual motion of plates, which proceeds at a few centimeters per year, an earthquake can move plates by several meters in a few seconds. And that movement can raise mountains, level cities, set off tsunamis, make the whole planet vibrate with seismic waves. So those are very destructive processes, but also very cool processes. And then there are also hotspots. So not all volcanoes happen at plate boundaries. Sometimes a plume of hot mantle material rises in what we call a hotspot. So the Hawaiian Islands are the result of one such hotspot that have been erupting basaltic lava for tens of millions of years. Plate tectonics has gradually carried the Pacific plate over the hotspot, therefore forming a chain of volcanic islands. In fact, you could see this chain in this sort of altitude map of the Earth. So the chain started up here near the Kamchatka region of Russia. I only know that region because of the board game Risk. And it went down here. Then the plate changed direction and went this way. And now, currently, the plate is really just sitting on top of the main Hawaiian Islands for a very long time. So the big island of Hawaii is the youngest. As we move back out towards the west, we get to the younger islands of the Hawaiian chain, where it's been more eroded. Then even further, we get to places like the Midway Atoll, which have been eroded so much that all that's left is a coral reef. This GIF kind of shows you what's going on. A coral reef is building up around the mountain. The volcano erodes because it's no longer erupting lava anymore, and we're left with something that looks like the Midway Island, the Midway Atoll. And in fact, in the future, it's going to be building a new island, which we've already named Lohi, the future in about 1 million years. Hotspots can also happen beneath continental crust. So, for example, a hotspot is responsible for the geysers and hot springs of the Yellowstone National Park. We also use the current motions of the planets to project the arrangement of continents millions of years into the past or the future. So, for example, at a speed of 2 centimeters per year, a plate will travel 2,000 kilometers in 100 million years. So we can then predict how the plates will look like in the future. So this video, which you can find on YouTube, shows you 300 million years into the future of the plates. One particular model of them, but still a very cool one. So we start off with the present day, but then slowly the plates move apart. Africa collided with Eurasia. Then Australia joined. So now the supercontinent is Afro-Euraustralasia. That's a mouthful. North America combined for a brief second to form Amasia. But now we're back to Afro-Euraustralasia. It's kind of fun to say. Antarctica almost joined. Now it's joined and we're formed Terra Orientalis. South America is completely detached from North America at this point. And now all of the continents are coming back together to form Pangaea Proxima in this particular model. I would like to point out, you should definitely replay this video again. During the entire 300 million years, Ireland and the island of Great Britain refused to merge with anyone else. So let's just say Brexit really, really worked in this particular model. So I'll end with just a few words. We've essentially, we should be able to predict all the geological features of terrestrial worlds we find around other stars. So if not, we'll have to learn more before we know whether other worlds could have Earth-like geology. So all of the worlds in our solar system, in our inner solar system, were heavily cratered during the heavy bombardment. But the extent of volcanism and tectonics has depended on planetary size. The interiors of the smallest worlds cooled quickly, so they have not had volcanism or tectonics for billions of years. The interiors of larger worlds have stayed hot longer, allowing volcanism tectonics to continue for much longer time periods. The major remaining question concerns whether fundamental properties can also explain Earth's unique plate tectonics. The lack of plate tectonics on Venus tells us that we cannot attribute plate tectonics solely to size, since Venus is so similar in size to Earth. However, if we are correct in hypothesizing that Venus lacks plate tectonics because of its high surface temperature led to a loss of water and lithospheric thickening, then a lower surface temperature might have led to plate tectonics on Venus as well as Earth. So, as we'll talk about next week, we'll trace Venus's high surface temperature to its nearness to the sun. While plenty of uncertainty still remains, it seems likely the broad geological histories of Earth and the other terrestrial worlds were indeed destined from birth by the fundamental properties of size, distance from the sun, and the rate of rotation. So that ends tonight. Pretty long talk, really took up the full hour there about the geology of the inner planets. Next week, we will talk about the atmospheres of the inner planets, and then eventually move to the outer solar system. So until then, thank you for watching. Make sure you comment below that you're enjoying this. Let me know that you're enjoying this. And otherwise, I will see you next week.